so that we can see what they're for, and then crack into the cycle stuff. And the cycle stuff is quite tricky. So again, ask me questions, stop me as we go along, and make sure we're happy. Again, we have a quiz due tonight, right? I'm trying to push the people along to take the quizzes. Make sure you're studying that stuff now and not tomorrow or Wednesday. You've got plenty of other things to worry about. So we started talking about Newman depictions, in which Newman decided that this was a very clever and simple way of looking at organic molecules. And what we're trying to do here is to get you to move between the different pictures, to be able to interpret the different pictures quickly so that you can get information from them. I can see here, looking at this backbone, looking at this chain, maybe on an exam question, you're given the name of a molecule, and you are asked to focus on a certain part of that molecule so you can decipher some information from it. By now, you should be able to look at that and give me this pretty quickly. Now, in the book, we do use these definitions, these abbreviations. They're okay, but I prefer to see these because that tells me that you know what those things are. You know what the substituents are. So these questions are kind of multi-layered. They're not just Newman depiction questions, they are nomenclature questions. Right, so you've got to be on your toes with these things. Down at the bottom, this is a more complicated picture than the ones we started with, because we have a discussion here of the different possibilities where the large and small groups start to interact. And it should be fairly obvious. What's bigger, an ethyl group or a methyl group? Ethyl, there's more stuff on it. As we build on the cyclohexanes, this will become more apparent. So having those two ethyl groups away from each other probably is a good thing, right? And as you start to rotate, be very careful. There's a way to do this without getting lost. And it is to keep one of the groups the same, keep one of the carbons the same. So in this example, the front carbon is being left where it is, and the back carbon is being rotated. And then the consequences of that can be discussed based on different energies. You can see now this is starting to get to be a bit of a problem because the two ethyl groups are getting close. What is that called when they're close to each other like that? That's the gauche conformation. And on the other side of this, we also have a gauche conformation, but this is problematic too because the ethyl is getting closer to the methyl, whereas over here it was next to an H. So you can do some fairly complex analysis here to be able to say what the molecules mostly will look like from scratch. Down here, what do we call these when things are on top of each other? They are eclipsed. They're not as good as the staggered conformations. Within the staggered conformations, you have the anti and the gauche. You have the anti and the gauche, and you've got to be on top, right? So you've got to recognize that this is very useful and it's not particularly straightforward. So I'm moving into the cycles. This is the second part of this chapter. And at the end of this, we have most of what we need to start talking about chemistry. Chapter 5 is a bit more definitions, a little bit more sort of nomenclature stuff, and then we're into the mechanisms. So cycloalkanes. How do you get cycloalkanes? You take a chain and you tie it together. You make it into a cycle. And that leads into some very interesting possibilities and some limitations. You find that chains just can flop around and they have all sorts of different possibilities for their shapes. But you put a cycle together, all of a sudden you have some rigidity. Okay, you can't do as much sort of rotation as you can with an A cycle, and that makes a difference in terms of their stabilities and also maybe their reactivities later. So this slide, introducing the cycles, is showing you some of the problems of the way we draw these things and also some of the limitations of what cycles can do. If you look at this, what would you call that molecule here at the top left? What is that? Three-membered ring with a cycle. What is it? Cyclo what? Cyclopropane. Now, cyclopropane has a problem because if you look at the hybridization patterns of the carbons drawn as they are, what does it look like? What should it be? What hybridization pattern? All single bonds. sp3. What should the bond angles be for sp3? 109.5. Now, there's nothing, that's nowhere near 109.5. That's going to cause a problem. If you have the model kit and you try to build cyclopropane, you end up breaking the bonds. You end up stretching them and distorting them to a point where it breaks. So cyclopropane is a pretty strained molecule, right? The key feature here on this slide is strain. This is a very strained molecule because the bond angles cannot get anywhere near what they want to be. It does exist, it's reactive, but that's the problem. Now, one of the limitations with the way we draw things in organic chemistry is that cyclobutane, if you want to draw it quickly, you just draw a square. Yeah? Easy enough. But that does not tell you very much about the actual picture, about the actual molecule. I'll show you in a second that it isn't a square, and it changes its shape to minimize its energy. Here we can see cyclopentane, where we've got 5 carbons. We're getting closer to 109, right? We're getting closer to the ideal angle. And then we seem to move to cyclohexane, and all of a sudden it goes out again. It goes to 120. I'll show you in a minute that the bond angles in cyclohexane are not 120. They're actually 109.5, which is why it tends to be the most stable molecule. As the molecule gets bigger, and you go to cyclopentane, cycloheptane, and cyclooctane, those angles change again. So the first part of this second half of the chapter is all about bond angles and the consequences of those angles on the stability or strain within the molecule. Now, graph at the bottom. What we're trying to show here is that cyclopropane is pretty unstable. It's quite high energy because of the bond strain. Cyclobutane gets better, and this is the energy per CH2 group. In other words, all you're doing going from left to right is adding an extra CH2 group, and you're looking at how that affects the outcome. Down here, all of a sudden the cyclopentane seems to be pretty good. It's not as strained, it's more stable. And the minimum is cyclohexane for reasons you'll see in a second. So what you should get from this graph is that there's a trend. As you head towards six-membered rings, they get better. As you head away from six-membered rings, they get worse, all to do with the bond strain. Now, in this example, or this picture, we're going to see very quickly that that hexagon depiction of cyclohexane is rubbish. It's a very quick, cheap way of drawing it, but it doesn't mean anything because the molecule certainly does not look like that. So what we've got to worry about is what do these things look like in reality? And I've got the molecular modeling program open, so I can show you that in a second. We can try and draw cyclopropane. If I do that, if I go over here and I build in Chem 3D, and I'm hoping you get access to this fairly quickly because it is very useful. If I type in here cyclopropane, we can look at it and move it. There's cyclopropane. Now, if you move this around and draw it flat like that, it does look like a triangle. That's how we would represent it on a piece of paper quickly, and it does actually look like that in reality. What we can do with this is minimize it. We can sort of relax this thing so that it does calculations to work out what's the best possible shape it can be at the lowest energy. That's a very oversimplified way of saying it, but that's what it's doing. Now, what I can do is turn this thing on its side, and if I do so, we can see some of the problems. Number one, there is no way those bond angles are anywhere near 109.5 degrees. That's terrible. That is a very, very strained molecule. But on top of that, and this is where you've got to be on, you've got to be studying hard, because I'm going to use Newman depiction ideas in these systems now. I'm going to apply that idea to these new systems. If I turn this thing on its end, look at the relationship between, let's say, this hydrogen here and this hydrogen here. Give me a term that describes that. They're eclipsed. They're right on top of each other. Is that good or bad? Bad. And you cannot avoid that in a cyclopropane ring. So that is building into a pretty unstable molecule. It's eclipsed all the way around. And there's nothing this molecule can really do to alleviate that. You can't get away from that shape. That's the shape of cyclopropane. Now, if you start adding extra CH2 groups, if I go to the next one, and I build up, in this case, cyclobutane, I have a four-membered ring. If I turn it on its side, just to give you an appreciation of where that box comes from, there's the four-membered ring right there. You can draw it like that, but it doesn't look like that. And you turn it on its side, you see maybe we've got some similar problems. What's the relationship between, let's say, this hydrogen here and this hydrogen here? They're eclipsed. And if you go on to the left-hand side of the molecule, there's some effort, some attempt here by the molecule to avoid that. Now I'm going to minimize this thing again. I'm going to run it through this program, this routine. And what it's going to try and do is twist to give the best outcome. It's going to twist to give the best situation where we have the least amount of eclipsing as possible. So I turn this thing around and I try to show you a little bit about what this looks like. We call it sort of a V shape. You can see here, this is a bit higher than here, which is a bit higher. This is a bit higher on the right as well. And you can see now that those things have tried to organize themselves to minimize the interactions. So the take home from this is that the pictures you see in a textbook at the beginning are quite inaccurate. There's cyclopropane, there's cyclobutane. This thing has moved, it has minimized to adopt a shape that gives you the best outcome. So we can see now the bond angle, 88, is nowhere near what it needs to be. That's why it's strained. But also now we have some possibilities of looking at relationships between hydrogens. What's the relationship between this H sticking straight up and this H sticking straight down? Give me a word from the Newman world that says anti. That's right, that's right. That's an anti-relationship, and that's a good relationship. Whereas if you look over here from the model I just showed you, they're almost on top of each other, but not quite. They're not quite eclipsed, they're not quite gauche. They're in between, and that's not the best situation. So those small rings are strained. We don't spend a lot of time on them. We spend a lot of time on 5- and 6-membered rings because we know a lot about them. So you've got two problems here, eclipsing and angle strain. Now you go to the cyclopentane, things start to get a bit better. We now have 5 carbons. There's much more flexibility in that cycle to be able to do things we want. And without getting annoying here, I want to go back to the Chem 3D and draw that one and show you what this will do. So again, cyclopentane. More complicated, yes. And this is a big problem now in structural biology, is the structures of 5-membered rings. RNA, DNA are all based on 5-membered ring platforms, If we knew an awful lot more about them, we could mimic those types of structures by making synthetic compounds. We haven't got the techniques to do that just yet. That's hopefully something that will happen in the near future. But I would argue that's more complicated. I've got more atoms. And I can think about how this thing is going to orientate itself to become the most stable picture. Now I've got two MM2 things here, right? Minimization tools right here. If I press the wrong one, it goes crazy. All right? But that's actually a decent idea of what molecules look like, right? They're very energetic and they're always flipping about, and it's quite a complicated picture. If I do the standard minimization, what it will do is just find its local minimum, its best situation, and that's what you're interested in at this point in your lives. If I move this thing around, I've got some problems, maybe. What's the relationship between this at the back and this at the front? They look like they're eclipsed. What about this one here and this one here? What do they look like roughly? Gauche, right? That's not so bad. It is a compromise to try and get the best possible situation with the atoms in hand. But these things, again, are becoming more complicated. So the cyclopentane certainly isn't just a pentagon. It is way more complicated than that. And as you'll see next semester when we do spectroscopy, this is a really big problem in biology. It's trying to work out what these things look like so that we can mimic them. We can do it with 6-membered rings, but we can't do it so well with 5-membered rings. So cyclopentane is a problem because of all the different relationships between those hydrogens. To go back and talk about the big one, cyclohexane, this is the one you'll spend the rest of the week worrying about. It is complicated. This is worth 2 lectures. I usually don't spend 2 lectures on topics. This is a complicated picture. On the top left, you have the standard picture that you learn straight away. You talk about cycles being possible, organic compounds can come together, the atoms can bond together and give you different patterns, different pictures. That is the standard shorthand way of representing cyclohexane. But as you'll see very quickly here, if you've been reading ahead, it's a way more complicated picture than that. It turns out that, as I'll show you in a second, that is a pretty poor picture. There are lots of problems with that picture. Everything would be eclipsed in that picture. That's no good. So this molecule relaxes to give something called a chair. And cyclohexane chairs, you think about biology again, you think about glucose as one of the most important organic molecules out there. It adopts a 6-membered ring chair. So we have to worry about that for later on for structural biology. This is conformationally flexible. This will do some pretty impressive stuff. On my website, I've got a couple of different things to try and introduce you to this. There's a YouTube video out there that seems to be quite popular across the planet to explain how this works with the models, to show you the actual movement of these atoms in space. Now, I'm going to spend today introducing this. I'm going to start again on Wednesday with a couple of videos to show you how it's moving, how the dynamics work, and then we'll finish off with more complex things heading towards the exam. So cyclohexane, not simple at all. If I look at Chem 3D again, I need to worry about 6 atoms now, 6 carbon atoms, and I need to worry about the conformational flexibility within that system that gives me a very complex outcome. So cyclohexane, 6 carbons, 12 hydrogens, very conformationally flexible. Where the small cycles are kind of tight and rigid, this guy can go wherever it wants. And you'll find now that there's some very well understood set pictures for what this molecule looks like. There's the 6-membered ring. If you look at that, there's the hexagon. That's how you would draw it if you're in a hurry. But if you're starting to worry about the structure and the sort of dynamics of this molecule, it looks more like this. Now, if I press the random MM2, it's had too much coffee, right? It's had way too much coffee. But that's what's happening in reality. These atoms are just everywhere, right? The vibrations in these are quite intense. And what it's done here is found some sort of place to stop based on whatever the parameters were for the calculation. But that's not what the molecule looks like in its best shape. Because if I turn this thing around, I might have some problems. I might not be perfect. I might not have exactly where I need to be to give the best outcome. So what I'm going to do here again is the MM2. And that will take me back to what's called a chair. So I'm going to try and do this as carefully as I can to lose as few people as possible over the next 15 minutes. And I'm going to look at the model display. I'm going to take out some of the atoms. I'm going to look at sticks. That is a chair. It's a lazy boy, right? Those lazy boy things that people like. If you sit on a lazy boy, you put your head here. That's the head of the chair. And you put your backside here. Okay? There's the seat of the chair. And you put your feet down there. Okay? That's what it looks like. You put a person on here, the head would go there, the rest of you would go here, and your feet would go there. That's where the chair comes from. Put it on its side, looks like that. Up at the left, this piece at the bottom is the chair, is the seat, and then down here is where you put your feet. So that is the basic structure of cyclohexane. It adopts the chair form, again, to minimize its energy. That's the best outcome. And we'll ask why. Well, what does that look like? Around that carbon, what shape does it look like? It looks like a tetrahedron. And what hybridization pattern are we asking for here? sp3, which is what shape? Tetrahedral with bond angles of 109.5. The bond angles here are 109.5. It's perfect, right? There's very little problem here in terms of any eclipsing or any steric problems. If I turn this molecule around and I ask about relationships of hydrogen atoms, what is the relationship between, let's say, this atom here and this atom here, approximately? They are anti, good, bad, or ugly? Good. What is the relationship between this atom here and this one here? Gauche, good, bad, or ugly? Good, fine. Yeah, not as bad as eclipsed. There is no eclipsing in this molecule whatsoever. So cyclohexane is perfect. It's kind of nice because carbohydrates, a lot of the exopolysaccharides on cell surfaces are six-membered rings, so we know a lot about them because of techniques that allow us to see these things, and we can mimic those things in pharmaceuticals. So the six-membered ring here is something you'll spend quite a bit of time worrying about and thinking about. It's easy to show you one-on-one. It's difficult to show 125 people in an audience like this, but if you come to the office or talk to Tyler, we'll show you how to draw these things and how to interpret them. So this thing looks complicated. This thing has a lot going on. If I turn it around, it seems to be the same shape. If I turn it upside down, it seems to be the same shape, all based on minimizing the interactions. So I'm going to leave that there and move back to the PowerPoint slides. So the problem with this is that we don't have a computer in front of us all the time to represent these things. You have a piece of paper. And you have to try and do this to the best of your ability by drawing pictures that represent those three-dimensional structures. Not easy at all. So what we're doing here, again, is conformation analysis. We recognize that cyclohexane is conformationally flexible because of the fact that there are 6 atoms in that cycle and they can move around related to each other. We'll see now that a very simple way of drawing a cyclohexane chair looks like that. And I would hope you would practice these things so that we can at least draw them in some sort of, rational manner. Practice, practice, practice. And we might represent also some extra detail. What do the wedges tell you? Things coming towards you. Now this should make sense because that molecule is not one-dimensional. That thing is actually three-dimensional, and it would be nice if we'd include these things to show that. Again, here's where you put your head. I'm absolutely rubbish at drawing, so just bear with me. There's where you put your feet, there's your arms, there's your beer, whatever you want. There's your lazy boy. That's how it works. That's a chair. So we've got to very quickly get organized in terms of the dynamics possible within this system. Again, why do we have to worry about this stuff? The straight answer is glucose. You don't understand this stuff, you can't possibly understand glucose and its shape and how it adopts its shapes in things like cancer metastasis, cell recognition, all these different processes that you have to be aware of later, many of you. There's a chair. What we'll try and do today is show you how this thing flips. It's analogous, those lazy boys, if you have the handle next to you and you pull that handle, what happens? Your feet go up and your head goes down, right? Are we all aware of these things? I've never seen one in my life before I came here, but they're kind of fun. You're sitting in your lazy boy, you've got your feet down, you've got your head up, and you pull the chair. You pull the lever, right? And your head goes down and your feet go up. What happens if it goes wrong? Your head goes all the way down here and your feet, and you flip. So today's all about flips. We're going to go through something called a boat, and we're going to go to a different chair form. So this I would contend is the most difficult class we've had so far. This is quite difficult, this is quite tricky. I want you to be able to draw these things and be able to discuss them in detail, rationally. So here we go. Pictures of cyclohexane. You have to practice drawing these things. There are some hints in the book I'll point out in a second. But we have to very quickly be able to recognize that each of the carbons in this cycle is tetrahedral. And that means something. That means that once you've defined the chair, you have other valences that need to go in there. And they need to be pretty decent in terms of their representation. On the top left, we have a chair conformation in which we have seemingly some atoms pointing straight up and some atoms pointing straight down, and we seem to have some atoms pointing out, away from the cycle. And it seems that on every carbon, you have one on the other. You have one sticking up and one sticking out down. You have one sticking down and one sticking out. And then you come over here and it alternates. We were up here, we were down here, we were up here, we are down here, we are up here. Why? How? Magic? No. This is basically the idea of the tetrahedral carbon. Every carbon has 4 valences. They are 109.5 degrees away from each other. That manifests itself in a cycle like that, like this. So I've got different positions. And when I start to move these carbon atoms, because this molecule is very conformationally flexible, I can form things like boats. I can move one of these atoms up, yeah? And if I move that atom up and I leave everything else where it was, I end up with something called a boat, in which all of a sudden, you know, there's a boat, there's the front of the boat, there's the back of the boat, there's the deck of the boat. Makes sense, right? And you can now imagine that this thing is a different shape to this. So this thing is not the same in terms of its energy. It is different. It's a different conformation, different shape. There will be some problems in this system maybe that make it less stable than where we started. And that's today's class, is to get your heads around how this thing changes its shape, how it flips. So we need to, you know, if you have the models, this really helps. If you have Chem 3D, it really helps just to get started. If you don't, come and ask. And we can start looking at compounds in a very detailed way, very quickly, to start getting lots of information out of these systems. What we are doing, whether you like it or not, a lot of people just don't get this stuff, don't take to it at all, is the beginning of molecular analysis on a level you really haven't done before. And I keep using terms like structural biology. That's where the big problems are, cancer, things like that. We've got to worry about how cells talk to each other, how systems go wrong. And often it's an understanding of shapes, or something as simple as that. So I'm looking down from this axis, and I'm looking at cyclohexane. And if you've been keeping up and you're okay with what we've done so far, you should be able to give me some ideas about relationships. What is the relationship between that hydrogen and that hydrogen? They are anti. What is the relationship between this hydrogen here and this one here? They are gauche. They are gauche. You don't see it, ask, get it worked out. It's there on Friday. It's there for the rest of the 2 semesters. It's not easy, not trivial at all. Well, what I would like you to be able to do in the near future, well, let's say by Friday, is to look at these compounds and then come up with something like that. That's a manipulation based on simply turning the molecule around, or, if you're better at this, putting yourself at an angle that you can look down those axes, and you don't have to turn the molecule necessarily, you can see what's going on. We've got now 2 Newman depictions put together. So we are looking down the bond axis from here to here, and the bond axis from here to here, and we have 2 of these things joined together. That's, you know, that's difficult. There's no doubting that's a difficult thing. So that's where we need to be, as soon as we possibly can. So we are looking at these things from, you know, a critical perspective. We're asking, what are the interactions between the different atoms? What's a good thing and what's a bad thing? In the same sense we did with the Newman depictions, what's good and what's bad. So we can talk about relative stabilities, and then overall, what the molecule would probably look like. Well, here we go. If you look at the boat conformation right here, and again, there's a thing on the website that shows you this in great detail, about 20-minute video showing you how this all works with the molecular models. If you look at a boat conformation, like this one over here, we've got some problems. We've got these 2 here starting to interact. These here are starting to interact. We're starting to get eclipsing. So if I ask you the question, which is more stable, the chair or the boat, what would it be? The chair, because everything was staggered. When you move into some of these other shapes, things start to get a little bit worse. But we're going to have to see by certainly Wednesday, that this motion is necessary. This flipping between up and down is necessary sometimes. What I have over here in the boat, again, you know, chemists have imaginations, I guess. If this is the boat and this is the deck, you know, there's the people on the deck. You can see here the flags at the front and the back. And those hydrogens are starting to get close to each other. That does not happen in the chair form because they're pointing in opposite directions. You bring this up, they start to get close to each other. And we have something called a flagpole interaction. And I'm going to use this again, this little pseudo Under Armour type thing. This means steric interaction. This means things getting close to each other. So that's a problem. Those flagpole interactions destabilize that system compared to where we started at the chair form. And we're very carefully depicting the different pictures that you have to worry about along the way during the ring flip. Hopefully in a few minutes I'll finish that ring flip off. Now, down here, how do you solve that problem? How do you make these two things get away from each other? Well, you twist. If I twist, maybe one of those H's goes to the back like this, and maybe one of those H's comes to the front like this, and they're away from each other. That's defined as a twist boat. It's simply another way for this molecule to relax a bit and for things to get out of each other's way. So you need to know what the definitions are for these different structures. And then we deal with this. And this can be a lot of fun, or it can be an absolute nightmare. You must look at this today. Okay? We want as many people passing this exam as possible. To help you do that, go look at this video. It will help explain everything I talk about today in more detail. This graph is something you should be able to reproduce. Do you memorize it? I would hope not. You've got enough stuff to memorize. Can you understand it? That's the idea. We'd like to be able to understand it. So the best situation is the chair, because why? Everything's 109.5 degrees, no eclipsing. Everything's staggered. That's great. Then we start to twist. We start to move things around. Things start to change. We have one end of the molecule, like the lazy boy, coming up, and things start to turn into what we call a half chair, because you imagine that, you've got your head here on the lazy boy, and you pull the lever and the feet comes up, right? The foot comes up. That's a half chair. You're on your way. And then we go further. That half chair becomes what we call a twist boat. I'll show you some pictures about what the problem is here, but it's fairly straightforward. What's the relationship between this hydrogen here and this hydrogen here? They're eclipsed, yeah? In that half chair, they are eclipsed. That's a bad thing. That's why it's so high in energy. So after that, it alleviates that by becoming a twist boat. We get another boat, basically close to that in energy, because you've got interactions that are being alleviated. And then we go to a next twist boat, back up to a half chair. And all that's happening here is the lazy boy screwed up. Right? You were quite happily watching the game with your head up here, and your backside here, and your feet down here. And then some joker came along and pulled that lever, and your head ended up down there, and your feet ended up there. Right? That's all it is doing that. Really, that's all it is. That's a ring flip going from one side to the other. Chair, half chair, boat, this comes back down, this comes back down. That's all it is. Lazy boy going crazy. But we have to know how to draw this, and we have to know how to discuss it. That's the hard part. The book has a rather, I think, convoluted way of drawing this thing, so that allows you to come up with a decent picture every time. I don't remember how I was taught to do this, but I would hope by now my chairs are somewhat decent. You know, that's what I do. That seems to work. It has to be approximate. It doesn't have to be perfect. It just has to look like a tetrahedron, so that when you put the different valences on, they look like tetrahedra. And I'll point out some problems. When you've drawn this and you've spent so much time learning how to do it, what's the problem with that? Anybody see what the problem is? Well, it's wrong. That's correct. But why is it wrong? It is certainly not a tetrahedron by any definition. Right? So that's bad. You just practice. It takes 10 minutes, learn how to do it, and make your friends. Okay? There you are. All the way around. And every one of them is tetrahedral. Every one of them has these extra two valences coming away from the cycle to give you that tetrahedral shape. Use the book's little technique there. There are other things on YouTube to look at to practice that, to be able to do it, how to do it, but let's get good at it pretty quickly. So the text here. Diagrams must reflect the fact that we're dealing with sp3 hybridization and that we are dealing with tetrahedral atoms. Once you've got that down, the rest of it falls into place. Again, just to summarize what we just talked about, this is the chair, this is the boat. We're going to find that this chair can turn into the other chair. This is where we're going now, the context, where this comes up and this comes down and this ends up pointing up and this ends up pointing down. That's the process that we need to deal with for the last part of class today. Again, why is this so good over here? Nothing's eclipsed. What is the relationship between this and this? Gauche. What about between this and this? Anti. Everything's fine. You work your way around that cycle, it's the same deal. No eclipsing interactions whatsoever. You start to drag this end up, you'll see now that you get to the boat, and one of the problems is this. What's the situation there? What do you think they look like? They look like they're eclipsed, exactly. Over here, maybe not so bad. Maybe we've got some gauche interactions, but we do have this problem. And we also have this problem, which is the two flagpole hydrogens, for those who are falling asleep. Don't do it. Flagpole hydrogens are in each other's way. So that's not as stable. It went up in energy. That's why it's higher on the graph. Feel free to say things, people. For those of you who are awake. Mark of the sea. Which atoms am I looking at? Well, what I've done is I've taken this atom. To get from one to the other, I have taken this atom, I've left everything else alone, and I'm dragging this thing up. You will see very quickly where those molecular models become useful in front of you to be able to do this. If I do that, this guy travels up to here, becomes this, and everything else kind of had to deal with it. Everything else had to get out of the way to make that happen. And then we have these consequences, where over here, this and this were quite happily gauche and ignoring each other. All of a sudden, they're on top of each other. They're eclipsed. That's a problem. Joe? Yes. This one here, or this one at the back? Yeah, yeah. If you'd want to draw a perfect, probably. I didn't make that. That's the book slide. But yeah, you're on the right track. If you draw that deck flat like that, they should both have the same interaction front and back, and that makes it less stable. And you will see that on this video that I made on the YouTubes. Colleen. Not on this planet. No, it has to go through this process, and we can prove it does. So let's worry about direction, let's worry about definitions, let's make sure at the end of this class today we know what a six-membered ring looks like, and we can talk about dynamics. We find now that as you put this thing together, every atom has one valence sticking straight up or down. And you go to the next one, it alternates. So up here, down here, up here, down here. It alternates around there. That's logical because you're putting tetrahedra together, and they can't all be pointing in the same direction, or else they wouldn't be tetrahedra. So now we get a pretty decent picture of the valence sort of display of a cyclohexane structure with all the carbons having 4 valences, 2 each of which are part of the cycle, and 2 each of which are now sticking away from the cycle. And these are the ones you have to spend a lot of time worrying about. They're different. Why are they different? Well, this one seems to be pointing straight up. This one seems to be pointing out. That's a fundamental difference in where those things are and what they look like and where they point. And that will lead to fundamental differences in their energy. So what we'll have to do here is define something. It's, if you're taking a geography class, this shouldn't be so difficult. What direction is this, people? In geography, that's north. And what's that? What's that? I have no idea. The argument here is that every carbon has a valence pointing up or down, straight up or down. And those are defined as being axial, as in the axis of the planet, the north-south axis. So if you're pointing straight up, you're axial. If you're pointing straight down, you're also axial. And it alternates around the cycle. This one is axial, this one is axial, this one is axial, this one is axial. Up, down, up, down. Whereas if you think about these other situations, for the second valence on each carbon, that definitely is not pointing straight up or straight down. It's pointing kind of out. That makes a difference. Ashley. That's where we're going in a minute. Don't jump ahead. That's now called equatorial. Why? Because this is a planet, and that's the equator. Okay? Who's got Emmanuel in lab? Anybody? Yeah, he's from Ghana, which is on the equator. That's the middle of the planet. That is defined as equatorial. Every atom that is not axial, it's fairly simple. Every atom that is not axial is equatorial, and vice versa. Right? So I've got up axial. Here's the hard part, especially if you don't have models or haven't got this in front of you. This Y certainly is not pointing straight down. But if you carry this on, I argue that is not going up. Is that okay? It doesn't look like it's going straight down, but it's certainly not going up. So this is now down. This is equatorial down. The next one along, the equatorial will have to be up. The next one along, the equatorial will have to be down, up, down. They alternate around that cycle. Not easy to see. Practice. So we've defined up or down, straight up or down is axial. Anything coming away from the equator that is not axial is then said to be equatorial. Now it gets tricky, because now we have to do this flip. This is going to be called a ring flip, in which this cyclohexane chair, lazy boy, whatever you want to call it, turns into this one. And we're going to find very quickly, listen to this carefully, big groups prefer to be equatorial. Big groups are more stable when they're equatorial. You'll see why in a second. In the text, they're trying to show this, and this is, I think this thing is confusing. You look at that picture, it's like John Madden. It's just like all over the place. It's like, what's happening here? That's why I did a video on YouTube for you to look at. Have I mentioned my video yet? Watch the damn video. Thank you. It's very difficult to show this incrementally on a piece of paper, because this thing is changing, and it's like a freeze frame. It's just changing and changing and changing and changing. How do you draw all that stuff? Well, it's difficult. The point here is that if you do this ring flip process and you drag this thing down, what was axial inevitably ends up equatorial. So if I'm up here and I do this ring flip, I end up like that. This is axial, this is equatorial. They change. Michaela. Yes, 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 yes. Any group that is axial and large might well want to be equatorial if it can. So what I've done here, watch this again for those who are not getting this, those of you who just woke up. This is being pointed down. That is now that atom. This is being pushed up. That is now that atom. That is overall the ring flip. In between, you have all the complications of the boat, the twist boats, and all that stuff. But we have a situation now where my axial thing now ended up in an equatorial position. Now for cyclohexane, where X is hydrogen, this is just going backwards and forwards. You saw my, the thing with too much coffee. It's just moving around all the time. It's going backwards and forwards. And if you had to think of it, focusing in on this picture versus this picture, for hydrogens, what is K for that process? If we're just dealing with hydrogens over here and hydrogens over here, what's K for that process? 1. Yeah? There's no difference because hydrogen is hydrogen and the stability on the left is the same as the stability on the right. It's the same. The problem arises when you start to get things bigger than hydrogen, which obviously is heading into more complex molecules like glucose. So with that in mind, we introduce some bigger substituents. And we think about the problems here. First of all, what is the problem? Well, if my group is axial, I have some neighbors that are quite close. And this is the key feature for this stuff. Those atoms, which are 1, 2, 3 atoms away from the fluorine in this case, are going to get in the way. That's a problem. That does not happen when you have the group equatorial. Those hydrogens are not close enough. So when your large group is axial, you get this problem. It's called a 1,3 diaxial interaction. That's really the driving force here, 1,3 diaxial interaction. And those things aren't good. If a group is axial, it will see its neighbors. It will see 3 atoms away, you'll have problems. How do you get away from that? You do a ring flip, and you end up equatorial, and then you don't have those problems. You're going to spend some time on this between now and Wednesday, and then we're going to look at it again. So there you have a fluorine. We have fluorocyclohexane. Now, fluorine is bigger than hydrogen. That's just a fact. It's not much. I'm glad I'm over here. It's not much bigger than hydrogen, but it is bigger than hydrogen. So in this example now, you're not going to get a K of 1 because one system is more stable than the other. One shape is more stable than the other. So on the left, it tells me from whatever measurement, whatever technique we had to measure this, 40% of these molecules have the fluorine axial and 60% have the fluorine equatorial. So you can work out an equilibrium constant, 1.5 if you like. You can work out free energy difference based on these properties, and we find that this is better. It's not a different molecule. It is still fluorocyclohexane. It's a different shape. It's like standing up or sitting down. It's still the same molecule. So you'd rather have this over here because all of a sudden my 1,3 problems have gone away. Okay, there's 1, there's 2, there's 3. They are nowhere near each other anymore. So this is good. We like it to be equatorial. What do you think happens as the molecule or the group gets bigger? Do I go back towards 1 for the equilibrium constant, or does it change? It's going to change. So if I change this to a methyl group, which is bigger again, you find now that only 5% of the molecules have the methyl group in the axial orientation. And the vast majority of them, 95%, have it equatorial. Again, because that's getting quite large. You can see here from my models from Chem 3D, that is pretty large, and it's certainly seeing its neighbors over here. So those 1,3 diaxial interactions are becoming much more important, and the system doesn't necessarily want to look like that. Now, question is, how does it get from here to here? What process is required to happen to get from there to there? The ring flip, yeah? Up and down versus down and up. That's all it was. That's all it was. Delta G here, there's a big difference now. Pretty big difference in those two structures in terms of their energies. And the equilibrium constant is getting bigger, 19. We're going to get to a point now where you can't go any further, and it's pretty much all one and not the other. But in this case, with a methyl group, some of it will be axial, but most of it will be equatorial. And this will play into Wednesday's class when I put 2 groups on and 3 groups on. And for the biologists and the people who are interested in medicine, pharmacy, whatever, glucose has 5 groups. So that's your world. We have to get there. starting fairly simply. So I'm going to go again. Isopropyl. What is an isopropyl group? Small, large, indifferent? It's quite large. In fact, there it is. Look at this now. There's a problem. That isopropyl group is starting to see and hit the atoms 3 atoms away. The 1,3-diaxial interactions here get to be quite problematic. That leads now to a very small amount of the axial orientation and a very large amount of the equatorial orientation. This is proof. We can measure these numbers. So large groups want to be equatorial. And we do have problems here now where it's even going to get worse, because you start putting something really big on here. Atoms can't be in the same place as each other. You can't have one atom in the same place as another. So the system is going to have to twist its way to avoid clashes. And that twisting, if we're starting off with perfect tetrahedra, 109.5 degrees, what's the effect of that twisting? You go away from perfect tetrahedra and you start to get more strain, so it becomes a bigger problem. In this case, K is quite large now, delta G difference is quite large, and you're starting to see the prevalence of one very much more than the other. T-butyl, worst of the lot. Notice this now, you've reached a limit. You're getting towards what we might call a detection limit. We have devices, you'll see next semester, to be able to measure things like this. You're getting towards the limit of detection. Can you see this stuff in a solution? And in this case, with 0.01%, pretty much none of that T-butyl will be axial. Why? Look at that. Wherever you put these things, they're on top of the hydrogens right there. That's a terrible situation. So this now, the delta G is huge. Think about the numbers here. And the equilibrium constant is huge. It's telling you that it's pretty much all this. And you can use that. You put a T-butyl group in a molecule of a cyclohexane system, it will go equatorial. And if there are other things attached, they will go where they are told. Right? T-butyl is the boss. So you put a T-butyl group in, everything else goes where it has to go, because the T-butyl group says so. There's the proof. You can see now twisting in the molecule. You can see problems, but this would much rather be over here, equatorial, because there are no diaxial interactions. What we've defined so far is shape. We've talked about the ring flip, going between one chair and the other, and we've talked about the consequences of the size of the group attached. Table here, just showing you those numbers. Same stuff that I just talked about. It's real and it's important. So there, the last thing I'll say today probably, that's what a 1,3-diaxial interaction is the communication across the cycle from atom 1 and atom 3 atoms away. That's a problem. We use this little symbol to describe that. That's a destabilizing interaction that will make your molecule less stable. How does this molecule become more stable? It does this. It does the ring flip process. Because then, in the other chair form, that X group is going to be equatorial, not interfering with anything, just pointing out into space, no problems. That is better. So let me mention this, a word of caution. Wednesday, I got 20 slides left. That's not an awful lot. But I'm going to spend every second of Wednesday talking about this stuff. You are required to look at that video, to read about this stuff, and to prepare for Friday, because it's on there. And I'll be through 4. This afternoon, I am busy until 3. If you're in recitation, fine, we can ask questions, but otherwise I'm busy.